All right. Good morning, everybody. I'm Paul Patras. I'm an associate professor at the University of Edinburgh. And today I will try to show you how we can harness the power of deep learning to make sense of mobile traffic. Why would you care, right? I think you should care because our cities are relying increasingly more on mobile connectivity. And I will show that the insights we can obtain from mobile network traffic can actually fuel a range of other applications in other domains. So I'd like to start by asking you to imagine in a sort of post-COVID era, you're on holiday in Milan, you're just sightseeing in a nice and shiny self-driving car that's electric, because Milan is decided to ban all fossil fuel cars in its cities. It's all going nicely. You're just enjoying yourself. It's nice and sunny. It's a beautiful city, and all of a sudden, car stops. You hit the traffic lights. Car wouldn't move. You try to restart the car. Nothing happens. You try to get through to customer support. The line is dead. What you don't know is that what has happened is there's been a sort of spontaneous march nearby. Thousands of people are streaming live video. And as a result, the mobile network connectivity that your car was relying on is no longer able to provide high bandwidth and low latency services. So now you say, well, this is kind of, this is a hypothetical scenario. But actually, this is not really remotely unrealistic. And why is that? Well, basically, what we have been seeing over the past years, and this is a trend that is continuing to increase, is the fact that we're seeing growing uptake of mobile devices and a surge in mobile traffic consumption. Yeah, so what you're seeing in this plot is basically an indication that we are looking at a fourfold increase in mobile data traffic consumption over the next 5 years, with a range of new applications, including augmented and virtual reality, file sharing, web browsing, and so on. So this poses some significant challenges to mobile operators, which could lead to infrastructure collapse of the sort I just mentioned. But at the same time, it also presents some opportunities. Yeah. So if the operators would be able to mine in an appropriate way all this massive big data, they will be able to understand exactly what kind of data is, or service, or content is relevant when and what location. So you could try to kind of manage networks a little bit more intelligently and avoid these catastrophic events. Now, if you want to gain understanding of mobile traffic, the first thing you need is measurement infrastructure. And this is quite expensive, and it needs dedicated equipment, which are typically referred to as network probes. And these network probes are deployed most of the times at the level of packet gateways, or PGW. And the problem with these gateways and gateway-based probes is that they only have limited knowledge of the location of a source of traffic consumption, or a sink, if you want. Yeah, so where a user is consuming or generating traffic. The alternative to that is to deploy more dense measurement infrastructure. So you could think about deploying these network probes at the level of radio network controller, or RNC. Now, the problem is with this approach that now you have a sort of an opaque view. You can't really understand whether there are any correlations that typically arise due to mobility. So the fact that demand for some service moves as the user moves through the city. So let's say you've got a mix of both. You have both gateway probes and radio network controller probes, and now you've collected massive volumes of data. You need to move them at some central location to be able to process them. So this is a big challenge. There's a lot of overhead that might jeopardize the quality of the actual service that you're actually trying to offer over the network. Secondly, wherever you decide to process this data as an operator, you have to have substantial storage capabilities to be able to aggregate all these measurements. And lastly, you need to combine them and do some spatial aggregation and have the right data analysis tools to make sense of this data that you've collected at so many locations. And the analysis typically takes quite a bit of time. So the problem is that by the time we've obtained insights from the measurements we collected, it's too late to make any meaningful decision based on them. The question is, how can we overcome this challenge? So basically what an operator would like to see is basically something similar to what you see here on the right. So this is a snapshot of the mobile traffic consumption, again, in the city of Milan. So you're looking at how people consume data across the city. Obviously, you'll have peaks at the city center and then maybe some clusters on the outskirts. So this is ideally what's needed, but obtaining this type of information is pretty challenging. So what the operator typically has to deal with is aggregate measurements that are collected most of the time at the level of gateway. So this is more or less what you see on the left. I mean, this is kind of scaled by the total traffic, but you kind of get the picture. You don't have this sort of fine granularity that you would need to understand exactly what's happening at a different place in that deployment. So it would be interesting to move from what we see on the left, just take this as an input and try to extrapolate or have some tools to basically infer what we're seeing on the right. The question is whether we should be using machine learning, and I'll try to kind of impress on you that this is the way to go. Now, this whole concept of moving from sort of low resolution images to high resolution images, or snapshots, low resolution to high resolution, of course, coarse grain measurements to fine grain measurements, there are some similarities here. Yeah? So we've seen this in the imaging domain, where you have an image of very poor quality and you try to obtain a high resolution counterpart of that. And this is similar if you're trying to do what my team has coined as, the mobile traffic super resolution term. So you have coarse traffic aggregate snapshots and you want to convert these into fine-grained measurements. So here, think about basically in a sort of a traffic snapshot frame as, the intensity of a pixel being the volume of traffic consumed at one particular location. Now, in both cases, basically, what we should be looking at is trying to learn the correlations between these sort of low resolution and high resolution frames. So how can we do that? So the approach we take is based on an unsupervised learning framework that is known as generative adversarial networks, or GANs. So the way this framework works is basically you have two neural structures. One was called a generator and the second one is called a discriminator. The generator takes the noise as input and is trying to output data samples that follow a target distribution. And the discriminator takes as input these generated samples and real sample, is trying to make sense of which one is basically a real measurement and which one was artificially generated. And these structures are kind of trained in parallel. One is kept fixed and the other one is trained, and so on. So it's kind of a two-player game. In the first case, you're kind of trying to generate data that is as close as possible to the target distribution and basically minimize the error between the two. Whereas the discriminator is trying to minimize the probability of thinking that an artificially generated sample is actually real. Now, in our case, we don't really need to feed the generator with noise because we have the coarse traffic measurements. So we kind of adapt this framework and feed coarse traffic measurements to the generator. And then the task of this discriminator is to understand if a sample is a true fine-grained measurement or something that the generator has produced. So let's maybe now try to sort of break apart the different components, the generator and the discriminator. So For the generator, we created a structure which we refer to as ZipNet GAN, and you'll see shortly why ZipNet. So the idea here is that basically you're taking a sequence of snapshots, which are basically low resolution traffic consumption measurements, and you feed them first. So you feed this to the generator. So in the first instance, the generator has a three-dimensional upscaling block. So here, basically, you're trying to convert the input into some tensors, vectors that have the same dimension as the output that you want to obtain, the high resolution version. And after that, we have a stack of convolutional blocks. So, I mean, for those who are not so familiar with convolution, just think about this as basically some mathematical operations that compute weighted sums across different parts of the input. So the weights are basically another function or a filter, so like sliding around this filter across the input. This is where the ZipNet comes from. So basically, we have a bunch of staggered skip connections, and if you look at this, basically it looks like a sort of a zipper. Yeah. So the whole idea here is that basically you're trying to extract increasingly abstract features about the traffic that you're observing, and now you're sort of building an ensemble system. So you're effectively sort of building multiple models, each of them having an output. And at the end, you have a sort of a voting system deciding which is the best possible output that will give you, you know, the best chance of guessing the right high resolution mobile traffic consumption snapshot. And lastly, basically based on the features that have been obtained through these multiple layers of convolutional blocks, you have another convolutional layer that basically transforms these features into the output, which is these high resolution measurements. Now for the discriminator, we just adapted a structure that has been used previously in imaging classification techniques. So this is a simple VGG net with 6 convolutional layers. Yeah, so you're taking the output from the generator that I just presented and the real measurements. And you just need to decide whether or not some input is the real one or an artificially generated one. Okay, so then to validate this approach, we go back to Milan, and we're looking at the data set that was collected by Telecom Italia over the span of approximately 2 months. And here, the coverage, the mobile network coverage is partitioned into a 100 by 100 grid. And what you're seeing here with the sort of the different squares is basically the coverage of a probe. Yeah, so we will refer to this as kind of upscaling instances. So this is what we will feed to the generator, the ZipNet. So it can be a 2 by 2 aggregated input, a 4 by 4 aggregated input, or 10 by 10, or a mixture of these. Yeah, so it might be that different areas are served by probes with different coverages. Okay, so just to pause briefly. So at this point, I should have convinced you that making sense of mobile traffic is kind of challenging. And there are some similarities with imaging applications which we can exploit. And I introduced this ZipNet GAN architecture. And I explained that we're going to look at some data set that was collected in a real deployment by Telecom Italia. So in what's left of my time, I will just show quickly some results. And finally, I'll make the case for using this methodology to solve a bunch of other problems in different areas. Yeah, so for the sake of comparing performance, we looked at a set of interpolation techniques that are typically used by mobile operators. We looked at a couple of image super resolution techniques, so strictly for imaging, and then we're looking also at a benchmark which uses deep learning for the same purpose. So we evaluated the performance of the ZipNet GAN in terms of three different metrics. One of them is the normalized root mean square error. And this is kind of an indicator of the prediction accuracy. So what you're seeing here with the different bars, different colors, are basically the different upscaling instances. So remember, the probes can cover 2 by 2 grids, 10 by 10, or a mixture. Yeah, so ZipNetGAN has the lowest error, which basically means that has the best prediction accuracy. And it works much better than interpolation or other deep learning tools that have been proposed strictly for imaging applications, because now we're performing this convolution here in 3 dimensions. Yeah, so we're scanning both space and time, because there are both spatial and temporal correlations that are characteristic to mobile traffic. And we can achieve reconstruction errors that are up to 78% lower. Another thing we examined was the peak signal to noise ratio. So this is typically used for images. So this is basically giving you an indication of the quality of the reconstructed frames. Yeah, so here basically a high value means good, unlike in the case of normalized root mean square error. And you can see that if we are just comparing against super resolution techniques that have been used for imaging applications, because we're taking into account these unique temporal correlations, we can achieve 40% higher fidelity when reconstructing the frames. And lastly, we looked at structural similarity index. So this is basically looking at how similar are the frames that we output, the high resolution inferences, with respect to the ground truth. And we're obtaining 36 times higher similarity between frames as compared to the other methods. Now, just a brief example here. Yeah, so of a sort of a super resolution instance. So on the right, you're seeing coarse grain measurements. This is what you feed as input to the neural model. On the left is the fine grain measurements, which is what we want to obtain. So below you see the results of the inference with ZipNetGAN. So you can see that basically they almost match, which is great. And if we were to do interpolation, for instance, by cubic interpolation, you could just basically capture the overall trend, but without being able to sort of capture the details of the traffic consumption at different locations. Another interesting question that arises was whether, what happens if the model is faced with some input that was never seen before. So think, for instance, of a football game on the outskirts of the city. All of a sudden, people are there and are just streaming a lot of video using social media, and there's a peak. And the machine learning model hasn't been trained for such events. So we wanted to see what happens. So basically, the input will look at as something similar to what you're seeing on the left. So it's aggregate measurements. You don't see that peak. You just see some blobs there. And the question was whether the ZipNetGAN would be able to kind of detect that peak. And indeed, it can detect the peak. This is what you see on the right. It cannot predict extremely accurately the magnitude of that peak, but you can still see that the structure is able to detect this previously unseen sort of abnormality. Yeah. So I'll close by saying that making sense of what's happening in mobile networks is interesting, but it can be used as a byproduct to make sense of other processes and phenomena in urban domains. So we could use mobile traffic super resolution to understand commute patterns, demand for transportation, if we're able to understand where people consume traffic and how that demand varies. And we're living in the COVID days, yeah. So understanding social interactions and data traffic consumption hotspots may be something that epidemiologists can use in their work on modeling disease spread. So I'll close by saying these are just some other applications where mobile traffic analysis can be beneficial to society. It's never too late to come and pose problems to us, which would be happily solved, and we're open to collaborations with other disciplines. So yeah, with that, I'd just like to thank you for your time and hand off to the next speaker.